Okay, hi everybody. May I ask to turn on your camera, please? Thanks. So the plan for today is to basically discuss and have a new lecture on pipelining. But before that, I would like to finish this multi-cycle. As Noah mentioned, we did not cover the jump, and it would be good to discuss that. And that's a good transition to pipelining. Again, to emphasize the idea of multi-cycle and also later on pipelining and all the topics that we will discuss until the end of this course would be one step how we could improve performance. And as you know, performance is very important, critical. We discuss about performance a lot in this course. So each new topic would be a new idea that has been proposed, in computer architecture in general, and has been realized, implemented in several machines. Some of them, for example, are really old ideas, but still few ideas have been proposed relatively recently. But most of the topics that we'll discuss is somehow old idea, but very important and fundamental ideas. Before we start, do you have any question to ask? You will hear about midterm grading and stuff hopefully soon. So I asked TA to grade them soon, pass the answers. I also looked at your answer. I'm happy that I saw some improvement. So clearly I saw difference that now we started mostly incorrect answers. Now it turns out mostly correct answers. So I was happy to see that. But again, after grading, if you have any concern, if you disagree with the grades, raise that through the system and ask TA to regrade it. Yes, Ross.
So just first off, would you be willing to release statistics on the exam? Just so we can get, if you're willing.
Yeah, sure, absolutely.
Okay. And just on that note, if a curve is warranted.
Yeah, definitely. I'll do the curve. Okay. As I mentioned, I would like you to do not worry about the great focus on learning, but again, there has to be some differences, right? But I definitely will curve the grades and so on.
Okay, thank you. I appreciate it.
Sure. Is there any other question? Okay, so if you remember, the key idea behind multi-cycle that enable multi-cycle is using this finite state machine, where we have different states and transition between states. So this finite state machine enabled us to have instructions that could take different number of cycles. So we don't need to enforce every single instruction have the same number of cycles. So if you remember, the key challenge in single cycle was that we had this limit that every instruction should take the same amount of time. But now clearly you see that in multi-cycle, different instruction could have different number of cycles, right? So for example, if like this is a partial view of the whole finite state machine for MIPS because it doesn't have all instruction. But imagine that, like for example, for load word, so we need to start by fetch S0, and then we need to decode it S1. As you see, like these two stages are shared across all other instructions. And then we have a conditional transition whether the opcode is load word or stored word to S2, which is about memory address, right? And then S3 is memory read if the opcode is load word. If the opcode is a store word, then we have memory write transitioning to S5. We have also S4 memory write back, and then again going back to S0. So for example, for load word, you see that we need 1, 2, 3, 4, 5 states, but for like other type of instruction, like for example for BQ, we have 1, 2, 3 state or 2-state transition or 3-state transition until we get back to a 0. So clearly, if we assume that here each state corresponds to one cycle, we could have we could assign different number of cycles for different instructions, right? So that is one of the key benefit of having multi-cycle, and the enabler for this multi-cycle is really this finite state machine that enable us to do this. And like if we want to add instruction, the only thing we need to do is to add the right states. And as you know, each state is nothing but just generating the control signals. You see each state contains some control signals that are generated carefully in order to enable this execution, right? So you can clearly correspond it to the data path, and you see what part of the hardware is activated, and you can do this each stage. For example, for addi, you need to generate, you need to have 2 additional states and the corresponding control signal. So in order to execute the addi and then write it back to the register, okay? And you know why we need a different state, because if you compare, for example, addi with R-type add that we had, you see the difference between the control signal, right? So the first control signal ALU source A is same, but source B, you see the difference. That's the difference. And as soon as we have different control signal, we need to have 2 different states, right? So for source ALU source B, we have 0, 0, and for source B in addi, we have 1, 0. And for ALU same way. So basically, we need to have different a new state for addi when we have immediate instead of a second register to add them together. This is true for other types of instruction. For example, for J instruction, right? For J instruction, we need to have a new combination logic, a new data path to enable that, because we are not able to execute J-type without this new data path. And this data path is simple, just marks where you have here, right? Previous, if you compare it with here, you see that without J, we had marks that had two inputs, right? To enable to either change the PC or write back to the register, right? But now we need a new we need to extend this mux to 3 inputs, where we need to, in addition to just incrementing by 4, also having a new PC, which is determined by the jump. You know, if you remember, jump had a argument in order to say, okay, what part of the memory we want the PC jump to. And if you remember the semantic of it, so we needed the bottom 26 bits shifted by 2 bits, right? And that's determine the address, and then write it back to the PC in order to determine the PC prime. So nothing unusual, very simple. And now we have, instead of 1 bit as a PC source, we need two bits, because previously we had 2 inputs. So 1 bit was sufficient. Now, since we have 3 inputs, we need 2 bits in order to determine the control signal. And then we add a new state. We actually have, we need only to have one new state, which we generate the control signal 10 for PC source, and we need to write back to the PC and going back to the fetch state. So nothing unusual, is very simple. And obviously, like since the previous one here, for branching, we assume 1 bit previously. So if you remember previously, we had 1 bit, 1 here. So since we extended the data path, we need to, if we need to adjust any detail in each control signal, we need to do that here. Like PC source, obviously we extended it to 2 bits, so we need to adjust this for branch as well, S8. But nothing unusual. You see that also for PC source as well in the fetch. So this is somehow semi-complete find out the state machine for MIPS. Do you have any questions so far? Hope this is clear. Yeah, and this is the multi-cycle MIPS processor with all data passes, and also the control unit with the corresponding control signal, and you see the connection with the corresponding components in the microarchitecture. And we had several examples, so I'm sure you can follow the whole data path and at least have a good understanding of the MIPS microarchitecture at this level, with this level of details. But multi-cycle again is not a perfect idea. Is one step improvement over single cycle, which enable us to have to assign different number of cycles to each instruction, but without further improvement, we cannot increase the throughput of the system. And the key challenge or the key shortcoming in multi-cycle without any further improvement is that it's still, again, is sequential. We do not increase the utilization of the hardware. If you think about it, like at each, like when we are executing each state, only a part of the microarchitecture is utilized. So only a small part of, for example, when we have fetch, only when we are executing the fetch, only part of the whole microarchitecture is utilized. The rest do nothing, right? When we are doing decoding, is the same. Part of this, the whole microarchitecture, the whole hardware is utilized. The rest is doing nothing. Essentially, we are not utilizing, we are not using the whole microarchitecture, the whole hardware resources in the best possible way. And there is clearly room for improvement, for gaining efficiency, for increasing the throughput of the system by some pipelining that we will discuss next. And the idea behind pipelining is really simple, is intuitive. We want to execute different, the key idea is to somehow find a way to utilize at least more part, not even all hardware in this microarchitecture, as long as we could. So if we could identify independencies, why not utilizing different part of the hardware for different instruction? This is very simple idea that we will discuss next. Pipelining that enable us to increase throughput and having a further performance boost for the system. But before that, here, like, we assume that each state basically takes one instruction, but this model, this finite state machine, has the capacity to enable us to even consider further more than or various number of cycle assigned to each stage. And the key modeling components that enable us to do so is just, again, transition between a state, but this time transitioning between a state where we are executing with itself. So basically adding a loop transitioning between each state. Like for example, let's say if we want fetch to have like say 3 cycles, we could add a transition between fetch and itself. We added because in finite state machine we could have these loops, right? We could have transition to one state between itself, right? So for example, fetching involve fetching from memory, and since memory needs more number of cycles, you know that it takes more time than like executing instruction using combination logic. Therefore, maybe we want to transition to decoding once we pass the adequate number of cycles, right? Because again, forcing each state to have the same number of cycles, then again, this is a limitation, because obviously the time that the machine needs to do each stage might be different. Fetching involve accessing memory, but execution only combination logic, right? So again, finite state machine enable us to have this design capacity in order to incorporate this into the model. So staying in the same state is one modeling capability that finite state machine give it to us. Okay, let's start the pipelining. Okay, so we discussed this, that we have limited concurrency. Some hardware resources remain idle during different phases of the instruction processing cycle. For example, fetch logic is idle when an instruction is being decoded or executed, which is not ideal, or most of the data path is idle when the memory access is happening, right? So these are the situations that we face because essentially each stage semantically is different and require different resources from the hardware, which these resources like located different part of the hardware, and we essentially make these artificial dependencies that each state needs to be executed, or basically we made this assumption that at each time one stage needs to be executed on the whole machine. So basically we created this assumption that we require the whole machine in order to execute each state, which is not clearly a good idea, and we could do better in this case. So we need more concurrency, or in other words, we need to increase the throughput or more work in one cycle. And the idea is to share resources, right? We could, as long as we could identify independent work, and that's the case. If you think about it, we cannot execute at the same time some dependent work. If two pieces of work are dependent on each other, Kirill cannot execute them in parallel. But if we are able to identify independent piece of work, we are able to share resources. We are able to use the same resource in order to execute things, in order to accomplish things. So we are able to, essentially the idea is to process other instruction on idle resources which are not doing anything. For example, when an instruction is being decoded, we could fetch the next instruction, because for fetching the next instruction is totally dependent on decoding. If you think about it, like for fetching, we require to access the memory. For decoding, we do decoding, right? We don't need that part of the hardware. So these are two independent things that we are able to use. When an instruction is being executed, we could decode another instruction, right? These are also two independent stages. When an instruction is accessing data memory, we can execute the next instruction. Again, this is memory access. This is using the ALU. And when an instruction is writing the result into a register file, we can access the data memory for the next instruction. Memory and register for two separate pieces. So we could use them at the same time. So again, in an abstract way, independent stages and idle resources. We definitely need to, we cannot execute two things. We cannot execute like, and this independence is not only at the stage level, but also at the instruction level. Like for example, if the next instruction requires the result of the current instruction, we cannot execute that. Or at least like maybe we are able to fetch it, but we cannot like execute it unless we have the result of the previous instruction. But as long as these are independent, and for now, don't worry about this independence. We discussed that how we could identify independencies between instruction. Mainly, this is the task of the compiler. But as long as we could identify independent instructions, we are able to do different stages of those instructions on the same hardware, different part of the hardware at the same time. And that's the idea behind pipelining, which we are going to discuss. Okay, we already discussed all of this. And the key benefit that we get is that we increase the utilization of the resources that we have, and by resource I mean the hardware resources, the whole hardware implementation of the machine, we are able to increase the utilization of that, and as a result, we increase the throughput of the system that you programmed. So as a result, you are able to finish more instruction per unit of time. That's the benefit that you get. So you see 1 over CPI. This is the key benefit that you get as a result. But obviously, nothing is perfect. There would be some downside. There would be some shortcoming that we will discuss, and the further ideas that we'll discuss throughout this course is trying to improve this downside of pipelining in some way. But don't worry about that. Now we discuss both sides, the good side of it, the benefit that we can get, and also the shortcoming, how we are going to resolve that. That's the matter of other topics. So this is what's happening in multi-cycle. At the top, you see that, for example, assuming that each instruction we require 4 number of steps or stages: fetch, decoding, execution, and writing back. Right. So in multi-cycle, we basically run each stage at a time, at a unit of time. So if you look at this vertically, only one stage is executing on the hardware, right? Either we are executing fetch or decoding or execution or writing of one instruction. There is no parallelism going on. So we need to finish the first instruction fully until we go and start the next instruction. Yes, Ross?
So like, could like a cascade happen if like one of these like fails, or like something gets through that's like bad because it looks like they're overlapping sort of? So if like, you know, not necessarily like failure, but a problem could cascade all the way through, rather than like, you know, I guess multi-cycle where you do each one in a step, but like you have a bunch of like other steps relying on the other ones.
Yeah, we will discuss some of these like potential failure later on as a result of this parallelism. Even though some of these potential failure might even happen without any parallelism. So that's a good point. So there is no perfect situation, and each idea, even though like increased performance, but again has some shortcoming, which this is again an ongoing work, right? So every like there are ideas, for example, for self-healing, how we could basically accommodate previous maybe failure of some instruction that has been executed previously for fixing things down the line. But that is a good point that you mentioned. In pipelining, as you see, the key idea is to execute independent instructions at the same time in parallel. So, for example, when we're decoding, the first instruction. So for example, when we start by fetching the first instruction, obviously we cannot fetch the second instruction. We cannot do fetching of any other instruction. Like the first thing, like that's basically the limitation that we have. Like, and obviously we cannot start doing decoding of the second instruction without fetching it, right? So that's the first step. Like we are bounded like of executing only one stage at the beginning. But then when we move to the decoding of the first instruction, we obviously can fetch the second instruction. And when we are executing the first instruction, we can start decoding the second instruction and fetching the third instruction. And when we are writing back to the register file or to the memory in the first instruction, we can execute the second, we can decode the third, and we can fetch the fourth, right? And like here, you see that like we are executing all stages at the same time. So here, the whole hardware has been engaged, and this is called steady state, where we are utilizing 100% of the whole architecture in one cycle. Obviously, there are some implicit assumption with this figure. And if you think about it, this assumption is that we clearly assume that each stage take the same time as each other. Like for example, writing back take the same time as executing, as decoding, as fetching, which is not clearly the case, which is not realistic assumption, but this is the assumption that we have in this ideal scenario. Okay, and we'll discuss this because life is not always beautiful, as this figure shows. But this figure demonstrates the key idea behind pipelining and how beneficial it is. And you see that like clearly the time to execute this 4 instruction has been decreased quite a lot. And we actually increased, we were able to use we were able to use 4 cycles per 4 instruction in the steady state, which is a good improvement, performance improvement overall in this example. And like, I mean, there are numerous different examples that you can think about pipelining, like in laundry or in factory lines, probably factory lines. You have seen it, where you can you can use the infrastructure for doing different things. For example, in the assembly line in factory, you can at the same time you can use the same resource to do different things for different, say, manufacturing things, right? For example, for manufacturing cars, some part of the pipeline manufacturing line could for example, let's say add something new to the car. Some other could could do something else, right? Could, for example, do some finishing, right? So at the same time, we are able to increase the efficiency and throughput of the system by sharing resources. Like, for example, in laundry, if we consider different stages, like placing the load into the washer, or using the dryer after we wash the clothes, and folding it and putting into the place that you put your clothes. Like, imagine we consider 4 stage. This is what happens in multi-cycle, even though we have different cycle for each stage, but we are not utilizing the resources efficiently. So we just wasted the resources, and there are obviously independencies between each stage. For example, when we are drying the clothes, we can use the washing machine for other loads at the same time in order to finish the whole 4 loads earlier, a lot earlier, comparing with doing this without any parallelism. And in this case, obviously, there is no dependencies between different loads. There are a bunch of different clothes that you want to wash. So no clothes waiting for the next load. And different steps do not share resources in this case. So we are able to ideally increase the throughput and decrease the whole time of finishing the whole task by doing pipelining, while we are, for example, drying the clothes of the first load. We could wash the second load, and so on. Like, while we are folding the first load, we are able to dry the second load and wash the third load, and so on. So we are able to increase the throughput 4 times as a result, and latency per load is, in this case, would remain the same, right? But latency for the whole task that you have, which basically consists of 4 loads, obviously has been decreased. But again, life is not ideal. Here we assume that each of these stages take the same time: washing, drying, folding, putting it back to dryer, putting back to the place you put your clothes, taking the same time. But obviously it's not the case. Typically, for example, say drying might take twice or 3 times more time than washing, right? So you are facing with a situation where you cannot really get the best throughput that you want to get. And like, for example, in this case, at the steady state, you were...
What if you had 2 dryers?
Sorry?
What if you had 2 dryers?
That's a good idea. Yeah, we obviously may be able to add 2 dryers, and that could increase efficiency if we are facing in this situation, right? But this means that we need to buy the second dryer, right? We need to or we need to pay more cost for the resources that we require. So in this case, as you mentioned, here we add 2 dryer A and B instead of using 1 dryer, and we are able to gain back the efficiency, the throughput that we want, but we are now using 2 different dryers and using new resources in this case. Basically back to the hardware, meaning that we added a piece of hardware in the microarchitecture, increasing the cost of the microarchitecture. Obviously, we gain performance, but we increase the cost. And again, this is the trade-off space that we have discussed previously, right? So this is a trade-off between cost and throughput of performance as a result. Good question. Good suggestion. So again, the goal is to increase throughput with little increase in cost, right? So again, like the easiest way, whenever we face this situation, the easiest way to fix this is to add more resources, but this add cost. So we want to decrease the cost or to maintain the same cost while increasing the throughput or minimizing the increase in cost. So really when we see a benefit by adding like few resources, that's fine, but like we don't want to add like new resources every time that we face this issue. So we want to maintain the same cost or increase as little as possible, but increase throughput the best way. So in this ideal pipeline, again, this is ideal because we have some implicit assumption, right? We assume that the same operation is repeated on the large number of different inputs, right? All laundry loads go through the same steps. Or we have a repetition of identical operation. This is one implicit assumption that we had. And also repetition of independent operation. So we assume no dependencies between repeated operation. This is also another assumption we had, because obviously dependent operation cannot execute in parallel. And we also, as we discussed, we assume that these sub-operations are partitioned uniformly. Basically, we assume that each state takes the same amount of time, but obviously this is not the case. This is a perfect scenario, having a uniform sub-operation. We want to get as close as possible to this ideal scenario, but reality is that we cannot get the ideal scenario. Is there any question? So, so in this scenario, if you think about it, again, this discussion is we are assuming that we are facing the ideal pipelining, right? So in single cycle, right, we have some combination logic. We do all of these operation, fetching, decoding, execution stuff, right, in one cycle. In multi-cycle, we basically we somehow now have the flexibility of doing these different stages in different cycles, right? So in the middle row, you see that like we separated the fetch, decoding, execution from memory access and writing back to the register or memory into different cycles, right? And we discussed that, like, for doing so, we need to, this gives us some flexibility, but we need to add new resources. We need to add some new piece of hardware in order to store the intermediate result, in order to again start the next step. Obviously, we can further increase this by like doing more granular splitting. Here, we further split it. Instead of 2, split it into 3. We separated fetch, decoding from execution, memory access, and writing back to the memory into 3 different stages. So now, now we increase the bandwidth 3 times comparing with the single cycle, right? But again, we are able to increase this number of independent stages as much as we want. We have this flexibility because of the capability of the finite state machine. So we can add more of these stages. We can make this as granular as possible. But this comes with some cost. Here you see that as we make this granular, more granular, you need new piece of hardware here, right, to store the result. So this is not the case that, and obviously not only cost of adding hardware, but also writing to this new hardware that we added, this combination logic, takes time, right? So it's not for free. We need to also consider this execution, incorporate this into the execution time or throughput of the system. So realistically, we have this delay that we impose to the system, this latching delay, or basically storing the intermediate result into new hardware that we discussed this previously to store the intermediate result. So so this scenario of like increasing throughput 3 times or bandwidth 3 times is ideal scenario considering 0 cost. But ideally, we need to incorporate the cost, and as we increase the cost, we need to incorporate this into the total bandwidth of the system. So latch delay in other hand reduces the throughput and somehow make it further away. comparing with the ideal throughput that we wanted to achieve. And that's one of the costs that we discussed, that like this is not ideal, and we have to live with it. So here, like, we added k number of these new hardware, and we need to incorporate that into the total cost that we have in the pipeline version, or k-stage pipeline version. Okay, let's also discuss some. Yeah, let me see how many slides we have. Yeah, let's discuss a few minutes about the instruction processing cycle. Again, like, one thing I would like to emphasize, that this, even though like you're familiar with this, so fetching, decoding, evaluate address, fetching operand, execution, storing results, whatever, you might see different version of this, right? Because when designing microarchitecture, depending on the designer, we might consider different stages, right? So we have the flexibility. Obviously, like, we need fetching, definitely we need decoding, we need some of these, but the designer of microarchitecture has the flexibility of considering different stages, right? And that's why sometimes you see different version of this throughout the lecture. So don't get confused. This is because of the flexibility that we have and different microarchitecture, right? But somehow, like, the basic or the standard version is that you see in different, most microarchitecture are these, like fetching, decoding, evaluating the memory address. Sometimes you see that evaluating memory address and execution are considered the same stage, sometimes not, and accessing memory and writing back the results. So, and if you remember, that was the single cycle microarchitecture that we had for MIPS, right? You see down here, correspondent to the previous slide, right? So everything needs to be executed in one cycle, but now we are able to divide it into multiple cycle. Here, for example, fetching takes 200 picosecond, decoding take 100 picosecond, and so on. And again, one of the non-ideal cases, ideally we would have wanted that each stage taking the same amount of time, like 200 picosecond or 100 picosecond, because clearly here you see that if each stage, by assuming that we want to execute each state in one cycle, then we are wasting 100 picosecond in decoding or in writing back to the memory, because like we have some stages that take 200 picosecond, right? So we have this this limitation that we need to have this cycle time of 200 picosecond if we assume that we want to execute each state in one cycle, but we could consider multiple cycle per each state, per each stage to fix this. But again, these are some of the limitations that we face when designing microarchitecture or when dividing it into multiple stages. And that's why maybe there might be some better idea of partitioning this, where we will discuss later on, like having more number of stages and having different boundaries, or like considering different number of cycle per each stage. This is probably more realistic version of what's happening in, for example, in pipelining, considering with this ideal scenario that we discuss in the example right here. You see that each stage taking different amount of time. So we are not assuming that each stage taking the same amount of time, and as a result, you see that we cannot get the full efficiency that we expected to get because of this. See here, like we have some waste here when we are, for example, when we are doing the second stage of the first instruction for fetching. Since fetching takes time, we have some waste here, or we have some waste also here and here. So we cannot get to the 4 times efficiency as we observe in the ideal scenario that we discussed previously. But again, here we assume implicitly that these instructions are independent, and you see that like we are loading different words. So obviously semantically these 4 load word, they don't have any dependencies between each other. And to repeat that, it is not trivial to identify independent instruction, because obviously in the program that you write, you have some dependencies between different instruction, and identifying this independent instruction is the topic of another thing that we discuss later on throughout this course. Okay, let's stop here. We'll continue more detail about pipelining, some ideas there on Thursday. I will stay here for a few minutes if you have any questions.
Excuse me, Professor?
Yes.
I wanted to let you know that I probably won't be able to make class next week or on Thursday. So I will catch the recording for that when I can.
Sure, absolutely.
I just wanted to let you know ahead of time.
Yeah, thanks. Thanks for letting me know. Yeah, sure. Thanks.